Okay. So, a man-made lake initially contains 200 gallons of water with 50 pounds of chemical dissolved into it. A solution containing 3 pounds per gallon of the chemical runs into the lake at a rate of 4 gallons per minute, and the well-mixed solution runs out of the lake at a rate of 4 gallons per minute. What is the maximum amount of chemical ever in the lake? Okay. So, with this equation, first we want to define our variables. So we know we're going to be defining this with time. Okay, so we'll use t as our variable for time. Then we have the quantity of chemical in the lake. So I'll define that as Q with respect to t. Okay, and then we know that initially at Q t equals 0, there is 50 pounds of chemical in the lake. Okay. So, based on the information in the question, we know the lake contains 50 pounds of chemical, and the reservoir has the size of 200 gallons of H2O. Okay. So, solution going into the lake is 3 pounds per gallon. Into the lake at 4 gallons per minute. We can take these two values and multiply them to get the rate of chemical going into the lake, which would be 12 gallons per minute. Okay, we know that the quantity coming out of the lake is a mixed solution at 4 gallons per minute. And we know that the quantity of chemical in the lake at this time is QT divided by the 200 gallons in the water already. Okay. So we will denote this as QT, and then this, we know that the rate coming out of the lake is 4 gallons per minute. We can take these values, multiply them by each other, and we will get QT divided by 50 pounds per minute is coming out of the lake. We can take the value coming in, the rate in, minus the rate going out, and this will be equal to the quantity, or rather I should say the change in the quantity of chemical in the lake at any given time in pounds. So right here we have a differential equation. We can move over QT divided by 50 to the left-hand side. So we're adding QT divided by 50 on both sides. We're going to get the change in QT plus QT divided by 50 is equal to 12. Okay, so now we can use the integrating factor method because we know that this is a linear differential equation. So we'll let I, with respect to t, be equal to e to the integral of 1 over 50 dt. This will give us I to the t equal to e to the t over 50. So using the integrating factor method, we can define the quantity of chemical in the lake equal to 1 over it, which would be e to the negative t divided by 50, times the integral of qt times the remainder bit. Okay, so this part of the linear differential equation, it would look like q prime plus qt with some coefficient equal to pt. So we're taking the integral of pt times it. Okay, so using u substitution, we could find that this integral is equal to 600 e to the t divided by 50 plus c. So if we multiply both of these values by e to the negative t over 50, this one will have a cancel out of e to the negative, or e to the t over 50, and we'll get 600, and then we'll get a negative c times e to the negative t over 50. And then we can use both of these values. We'll define the quantity of chemical in the lake at any time. This is our general equation. Okay, so we know initially at time 0 that there's 50 pounds of chemical in the lake. We plug both of these values into the equation so that we can solve for c. Move our values over with algebra, and we'll find that c is equal to 550. So our general solution for quantity of quantity of 50 pounds of chemical in the lake at time t would be equal to QT is equal to 600 minus 550 times e to the negative t over 50. Okay, so we can see that with increasing t, this term right here will be decreasing. So this second term is decreasing with increasing t. So what we wanted to find is the max quantity of chemical in the lake. So what we can do is we can find a critical value of q prime of t. So if we take q prime of t and we were to take the derivative of this term, we'll take, okay, so we have e right here, we have t, the coefficient on t is 1 over 50, we'll take the derivative with respect to t, so we'll take that term and move it down here, and it'll be negative 550 times negative 1 over 50 e to the negative t over 50. So our derivative term, if I can find our derivative term of qt, q prime of t, will be equal to 11 times e to the negative t over 50. Okay, and to find the critical value of this, we want q prime of t to go to 0. So, looking at this, we can see that if the term with e has an infinitely increasing value of t, this term will divide 11, making it resemble 0 more and more as t goes to infinity. So we can say that with decreasing, this term is decreasing with increasing t. So we can mathematically represent this as t goes to infinity, the limit of qt, this term right here, will approach 600, since this will approach 0. With this will be the maximum quantity of chemical in the lake. So this solves our differential equation.